Hello students, this is our next video tutorial on related rates. This is a challenging topic for students, so we'll do lots of examples on this. This video will go through a single example just to provide you with some general background so we can hit the ground running in class tomorrow. Our goal here is to understand how when one variable changes, so we're talking about the rate at which a variable changes, it has some effect on how other variables change. So we're trying to understand how to relate rates to one another. That's why it's called related rates. Oftentimes we will be interested in a rate that is the speed of something, how fast something changes. And as soon as we say the word fast, we are describing that time is related in some fashion. So before we get going, we'll do an example with implicit differentiation to remind you of this topic, as it will play a central role in applying related rates. The example here is we want to find the derivative of y with respect to x of the expression 3x squared plus 2y cubed equals y. Now when we say find the derivative of y with respect to x, we're saying how does y change when x changes by 1 unit? So the variable y is being related to the change in the variable x. So the change in the variable y is being related to a fixed change in the variable x. So if x changes by 1 unit, we're asking how much does y change? To solve this problem, we need to realize that the chain rule applies. So we will brick out the y variable. Now when we take the derivative, the first piece is the derivative of the brick. So we'll see the y primes appearing here. And to emphasize that the change in y is being related to the change in x, we'll use the dy dx notation. Our next example is to find dy dt. So we're letting t change by 1 unit and asking how does y change. This is a bit different because you'll notice that t does not appear in this expression at all. This is the same expression as we had before. Now when we want to find the derivative, we realize that both x and y may change as t changes. So the chain rule must be applied to both x and y. So we read those out, and then we begin the chain rule by starting with the derivative of the brick. So we'll have an x prime in the first term and a y prime in the second term. And now we'll return to the notation dy dt or dx dt as the case may be. When there's only a single derivative, as in the case on the left, we would solve that for dy dx. As on the case on the right, it depends which variable you're interested. Are we interested in solving for dy dt, or would we be interested in solving for dx dt? That would determine which variable we solve for. So let's move on to an example of related rates. Here we're blowing into a balloon. That balloon will expand. We're blowing at a constant manner, so we don't blow hard, blow soft, blow hard, blow soft. We blow at a steady rate. We'll say that that rate is 10 cubic inches per second. Now the balloon's going to get bigger as we do this. So things like its radius, its diameter, its surface area will all change. And so the question we'll ask is, how fast are these objects changing when we blow air into the balloon? So a summary here is that we're blowing air into the balloon, so we're changing its volume. And these other variables are of interest to us. And since we're blowing air at a particular speed, time is also a variable that is of interest. And we see that appearing in the units of how our volume is changing because it's compared to the change in volume for every minute that changes on the clock. So we'll ask, how fast is the radius increasing? To begin to answer this question, we need a relationship between these two important variables. Volume, that's the information that was provided, information about the change in volume, and information that we desire, which is regarding the radius. If you remember from high school algebra, you might recall the volume of the sphere. We will assume that our balloon takes the shape of a sphere, and that this volume of the sphere is given by this expression, 4/3 pi r cubed. Now we'll use this relationship to find a relationship on the rate, how the rate of V, the rate of volume, is changing in comparison to time. So we have that dV dt is 10 cubic inches per minute. We'll work with this expression on volume, and we'll want to find the rate at which the radius is changing, so we want to find dr dt. So notice we don't have an expression with these rates in them. We're going to have to take this expression of volume and radius and create an expression on the change in volume and the change in radius. So first, we start with our relationship. Now to create a relationship with these derivatives, we're going to need to prepare to take a derivative. Because we want derivatives with respect to time, any variable that's not time, we will need to apply the chain rule. So here we've read it out, we've bricked out those other variables, both v and r. So we're ready to take a derivative now. As we know, we always start with the derivative of the brick. So we'll have v prime equals, and on the right side we start with the derivative of the brick, so r prime, and then the derivative of the frame of that window, what's left, the derivative is 4 pi r squared. So that's the chain rule. Now we want to return to these the notation that emphasizes time. So we have dv dt is equal to dr dt 4 pi r squared. And that is the crux of finding a relationship on the rate of variables, applying the chain rule in this fashion. So now if we simply solve for dr dt, because that's a variable we're interested in, we divide by the 4 pi r squared and we have this expression. So now we'll use this with some numbers here. Notice that we have this expression, but it also includes the variable r. And that makes sense. As the balloon changes, well, depending if the balloon has a lot of air in it, then when we blow in a little bit, r won't change by very much. If the balloon is quite small, when we blow in the air, the balloon's going to expand quite a bit, and the radius will increase quite a bit. So we should expect to see r in this expression. Here are two examples that illustrate that concept. First, we'll look at how the radius changes when the balloon has a radius of 2 inches, and then how the radius changes when the radius is 5 inches. So all we're going to do is evaluate this expression when r is 2, and we'll also need to evaluate the derivative of volume at its value, which was 10. So if the radius is 2 inches, we see that the rate at which the radius changes is 0.1989. If we evaluate it when the radius is 5, we get a different value, of course, and that value happens to be 0.0318. Okay, so when the balloon is large and we add air, let's say we blow air for a second, t changes by 1 second, then we don't see a very big change in radius when compared to when the balloon was small. Finally, let's just talk quickly about the units for dr dt. R was measured in inches, while t was measured in seconds, and so their ratio is measured in inches per second. It's that simple, okay? Inches per second. In another way to see this, let's look at the expression we had for dr dt. We know that the volume changes in cubic inches per second, so that's cubic inches per second there, while radius is in inches. So we have inches per second in the numerator for dr dt, and square inches, because you'll notice the r was squared, in the denominator. Now the inches squared will cancel off with 2 of the inches in the numerator,